Hello and welcome. In this lecture, we shall discuss the constitutive equation for the stress tensor T. In order to motivate our discussion, we shall begin with a simple case of a static fluid, move on to Euler's perfect fluid, for which the constitutive equation is particularly simple, and then finally take up the linear Stokesian or Newtonian fluid, which will ultimately lead us to the Navier-Stokes equations. So our topic for the day: let's just put it up here. Equation for the stress tensor fluid. Okay, so before we start discussing the constitutive equation, let's just revise the two equations that we have derived so far. So, for an incompressible fluid, we have the principle of conservation of mass that leads us to the continuity equation. It says that the divergence of the velocity is zero. This is the first equation. And then we have Cauchy's equation of motion that we derived in the previous lecture. It takes the form the Lagrangian derivative, the velocity, times the density, which is the acceleration of a material point, is given by the divergence of the stress tensor, and we have a contribution, of course, from the gravitational body force. Yes, so these are our the two equations that we have. Now, if we ask ourselves what are our unknowns, well, we have certainly the three velocity components, and then we have the six stress tensor components. Six, of course, because you remember that stress tensor is symmetric, so that means three of the components are just same as three others. So instead of 9, we have six unknowns. So we have three velocity unknowns. We have the six stress tensor unknowns, and the density we assume at this moment be known by independent means measurements. Right, so you can see that we have 9 unknown quantities now, but we have only a total of 4 equations, because this is a scalar equation, divergence of velocity giving us a scalar. The Cauchy equation of momentum is a vector equation, so that's 3 different equations, the components of velocity. In total we have 4 equations, but we have 9 unknowns. So clearly the problem is not closed. We need more information to be able to solve the equations of motion. And as we discussed in the previous lecture, this is actually a good thing, because you see that the theory as it stands right now should be applicable to all fluids equally well, because we've not made any assumptions about the nature of the material that we're studying in applying the conservation of mass and the conservation of momentum, or the linear momentum principle. And in fact, the only material property that is entering the equations right now is the density. So the equations as they stand would lead us to believe that fluids, provided they have the same density, would behave the exact same way as far as flow is concerned. But clearly this is not what we know from experience and from laboratory measurements, because we can in fact create fluids, and they are available, which have this very similar densities but wildly different viscosities. You can take the example of the commercially available different grades of silicone oils, where you can vary the viscosity by orders of magnitude without changing the density too much. And from there we know that, for example, the flow behavior in a pipe for a low viscosity version could be unsteady and in fact turbulent. The high viscosity version could be laminar. So clearly there is more that determines the flow of a material than just its density. And this is where the stress tensor and its relationship to the velocity field will come in. So in this sense, we have both a mathematical reason to look for more information about the stress tensor just because the system is unclosed, and also a physical reason. That is, we need to have a way in which we can input the material properties of the fluid into our equations, and that route is going to be provided by the constitutive equation for the stress tensor. Now, before I go further, it's also relevant to point out that the governing equations, that is, the equations I've written down before you, the conservation of mass and conservation of momentum, these are what this comes closer to being what we would consider a physical law, in that they are applicable to all materials, and they are based on a fundamental axiom about conservation of mass, the conservation of momentum. Thereby applying these fundamental ideas using the mathematical framework for describing a continuum motion and the continuum stresses, we can write down the equations in the form that we have before us. So these have the status of a law. On the other hand, the constitutive equations that we are going to propose and use that relates T stress tensor to the velocity field, these aren't really basic physical laws, rather they vary from material to material. And in fact, if we live entirely within the continuum world, there is no real way to derive a constitutive equation purely from continuum first principles. Indeed, ultimately, this means that we really have to guess the constitutive relationship, as we will see in this lecture. And these guesses, of course, can be extremely quote unquote educated by using mathematical thinking combined with ideas of symmetry, principles, and so on that can guide us in the choice of such a relationship between stress tensor and the velocity. But ultimately, it won't be based on fundamental first principles. One needs to verify them in a laboratory, and they would differ from material to material. So their status is quite different from that of the governing principles of mass and momentum conservation. So yes, this is something to keep in mind, and this is sort of the difficulty, let's say, of continuum mechanics, that we need extra information in order to close the problem. Now, there are some fluids for which we can write down a statistical mechanics model or framework uh, based on the molecular picture of the fluid, and then we could ultimately hope to derive a relationship between stress tensor and velocity from the molecular underpinnings of the material. But this has been possible only for very simple cases. For example, the case of an ideal gas, where the molecular picture is just billiard balls bouncing around. And for a few other situations, it's possible. But by and large, that program also remains impracticable because of the difficulty of doing the molecular simulation. So the current status is that we have some information from statistical mechanics in the case of a few fluids. We have some guidance from the principles of continuum mechanics and the mathematics of symmetry. And by a combination of these and by using certain intuitive ideas, we have been able to come up with constitutive equations for certain classes of fluids, which ultimately, of course, have to be verified by experiment by comparing predictions of the continuum model for flow rates, velocity fields, pressure fields, and so on with what's observed in the laboratory. Having said that, what we will see lecture is that thankfully almost the simplest constitutive equation one can write down, which is consistent with basic ideas such as invariance to change of a coordinate frame and so on, that the simplest such law turns out to hold for a large variety of liquids. And we will also see why this should be the case, but that is indeed quite fortunate. And so that is what would lead us to the Navier-Stokes equations we use for a whole range of applications. All right, so with those preliminaries out of the way, let's begin with our discussion of the constitutive equation for the stress tensor. So we will start, as we've done so far in these lectures, with looking back to history and seeing how the idea developed. So because that's also a nice way to understand and to get a physical idea of equations that we're looking at. All right, so let's begin with the simplest case of static fluid. So here we mean the fluid is perfectly at rest or at mechanical equilibrium and is not moving. So problems in static fluids occupied everyone from Newton to the Bernoullis to Euler uh, intensively, and they worked on several different special cases. Examples include the shape of the Earth as a state of equilibrium between gravitational and rotational centrifugal forces. The fluid in that case was taken to be static, and the problem was to determine what would be the shape of this object uh, that would result from the equilibrium. Another problem, and of course, Newton was the first to attempt a solution, and he uh, did correctly guess that the poles would be flatter, and so the Earth shape would deviate a bit from a sphere. But his answer was not entirely accurate, and his reasoning was not entirely sound. But that problem found a basis for several of the works to follow. Another problem that occupied quite a bit of attention was problem of calculating the forces exerted on the walls of a cylinder containing a static fluid. So imagine you had a fluid here, the cylinder, which you have a fluid at rest. Yes, and one would like to know what is the force that is exerted on the walls of this containing vessel, because then that would help you design the thickness of the walls, for example. In fact, such fluid containers typically have walls that thicken as you go to the base, because as we now know, under hydrostatic pressure, the forces exerted at the base is greater than the forces exerted at the top, just because of the weight of the fluid. But even this simple idea wasn't clear in the early stages of fluid mechanics. So such static fluid problems occupied many of the thinkers, and ultimately it was Euler who realized that all the special results derived for problems such as the cylinder and other static problems could be brought within a single framework if one were to make the hypothesis that the surface stress acting on any arbitrary oriented surface would always be normal to the surface and act inwards. In other words, what he postulated was Euler's, let's say, hypothesis for a static fluid was that the stress vector T of n, that is, let's draw a surface. Imagine you have a material volume within a fluid. Everything is static. And he wants to know what is the stress on this surface n, what is the stress on this surface n. And what he said was, in either case, at any given point, regardless of the orientation of the surface, the stress Tn would always act inward, that is from the outer fluid to the inner fluid, and would be directed along the normal, but oppositely so. So he wrote down P is minus n unit normal. T is a vector, of course, times a scalar we call the pressure, which we today would also identify with the pressure of a fluid at equilibrium. So he said that the pressure could be a function of space, as it is, for example, in the cylindrical problem. But at any given point, so let's say at this location, where the pressure is defined P, then regardless of the orientation of the surface, this pressure would stay the same. And the stress vector would always point the opposite direction of the normal to that surface. So to understand the implication of this, this is basically, as you can see, possibly the simplest way of specifying it. You do say that the stress vector depends on orientation, which clearly it must, but you say that it's simply directed along the normal to a surface, regardless of the orientation of that surface. So let's see what this means if we substitute this into the Cauchy equation of motion. For the case of a static fluid, that means the velocity is zero. In order to do that, we should first write down what the stress tensor is. So for the stress vector to have this form, then remember the stress vector is n dot t. So t is n dot capital T. So the two of these imply together that for a static fluid, let me say static stress tensor for a static fluid should be minus the pressure times the identity tensor, which basically means that you have diagonal tensor minus P along the diagonal, zeros everywhere else. So this is our stress tensor for the case of a static fluid, as Euler hypothesized. And now if we substitute this into Cauchy's equation along with the fact that V is equal to 0 for a static fluid, we will simply get the divergence of minus P times the identity plus rho G equal to 0. That in turn implies that the negative of the gradient of pressure, so you can show that the divergence of the identity simply becomes a gradient of the pressure plus G equal to 0. And now for the case of our column of fluid we had drawn earlier, let's say we fix the bottom as the origin with the z-axis pointing upwards. Let's say the surface of the fluid is at a height capital H. Then, and also let's take the pressure here, P0, some reference pressure at the surface. Or to be more precise, we can say it is just the atmospheric pressure at the surface. And we would like to know what would be the pressure somewhere here, so that we can calculate the pressure force exerted along the walls. So all we would have to do is solve this equation, integrating it from z equal to 0 to the height capital H, applying the boundary condition that the pressure is atmospheric at z equal to capital H. This would lead us to the following expression for pressure as a function of E. Sorry, I have lowercase. Pressure as a T must then just be equal to G Yes, so here of course I use the fact that G vector is simply scalar G times Ez, just a scalar now. This is what we have. And this is what you would expect. It's basically hydrostatic pressure. You carry the weight, so the pressure balances the weight of the fluid. At Z equal to H, oh sorry, I missed out plus the atmospheric. So at Z equal to H, the pressure is just atmospheric pressure, and as Z decreases towards 0, we have the pressure increasing. Do I have this right? I think I made a sign. Yes, of course. There should be a negative sign. So at Z equal to H, the pressure is pressure atmospheric, but as Z decreases towards 0, you see you have P atmospheric plus essentially if Z is 0, you have P atmospheric plus rho G. Alright, so this is something well known. So essentially the fluid static equation says that the pressure gradient, which is acting in this case upwards, because you see the pressure is increasing downwards, so negative the pressure gradient acts upwards, and that upward force balances the downward force of gravity. Yes, so gravity acts in the negative z direction. Alright, so this is the well-known result, and the point is that Euler was able to arrive at the correct result in this case of a fluid, a cylinder containing a fluid, and one could also calculate the shape of the Earth correctly by accounting for centrifugal forces and using the appropriate static equation and so on. Of course, that's the limit where the fluid is, the Earth is considered to be just a rotating fluid. So the point is that this simple idea that all stresses act purely normal and invert to a surface worked quite well for a static fluid. But now, of course, the problems of the day were beyond static fluids as they are now, and one would like to calculate the drag experienced by a solid immersed inside a moving fluid, or the pressure drop required to pump fluid through a pipe. These are problems that occupy us even today. Euler then had to or wanted to deal with a moving fluid, and he thought the simplest thing to do would be to see what happens if we extend the static fluid constitutive equation to a moving fluid. And so he came up with the idea of a perfect fluid. For a perfect fluid, which is, as we now understand today, a fluid that is essentially inviscid, which doesn't have viscosity. So for such a fluid, you retain the same constitutive equation that would hold for any fluid if it was static. We say now that that's also true for the motion, provided the fluid is perfect. So in this case, now the Cauchy equation of motion becomes, now remember we are considering a flowing fluid. So we would have dT, material derivative, equal to minus gradient of pressure. And you see that when Euler applied this idea of a perfect fluid, and he already had his equation of motion. Of course, he didn't know, Euler didn't have Cauchy's equation of motion, he didn't have the general idea of the stress tensor. But he could arrive at this equation by directly postulating simply that all the surface forces act normal to a surface. And so he arrives at this equation, which we today know as Euler's equation of motion, which is applicable to an inviscid fluid, or as Euler would have it, a perfect fluid. So this equation today has a wide number of applications to flows that are far from walls, flows in which viscosity doesn't play a key role, even though the fluid has some finite viscosity. So by this we mean applied in several atmospheric motions. It's used to describe waves on a free surface. It was used to describe tides quite early. However, these applications didn't take place in Euler's time. In Euler's time, we were still worrying about, mainly concerned about flow through a pipe. So the Euler's equation didn't find its natural domain of application uh, during Euler's lifetime. And so by the standards of normal science, or rather the perception of science, where we have to always match with experiment immediately, Euler's equation would have been considered a failure at his time, and his entire program might have been thought to be a failure, as indeed some did think, as the communities of fluid dynamicists or mathematical fluid dynamicists were separated from the hydraulicians who used to come up with empirical formulas for the engineering problems that they had to solve. But nevertheless, as we saw, if one is patient enough and continues to follow the mathematical thinking logically and rigorously, even though it takes some time, one can eventually reach an agreement with the experiment and that bears fruition. So Euler should really be congratulated for carrying on his program diligently, even though he did not see immediate success and immediate verification with the experiment. Okay, so where does Euler's equation stand up in problems? Well, as we know today, this equation would give us very bad results if we were looking to understand flow through a pipe. Of course, because here, let's say there's an applied pressure gradient Pn, and there's a different pressure gradient P out. So if Pn is greater than P out, we expect the pressure to flow under the applied pressure gradient. Sorry, the fluid to flow. But Euler's equation would have no way to account for the drag that the fluid experiences at the wall. Because as you know, the stresses that Euler could take into account was only the normal pressure forces. He had no way to take into account the drag force, let's say F drag, which would act tangentially to fluid elements that flow past it. So this is a purely tangential, as we would say, shear force. The drag force is a tangential shear force that cannot be accounted for by the Euler equation. Cannot be accounted for by stress tensor being purely normal to a surface. So, what this problem such as this highlighted early, that one needs to generalize the constitutive equation, or rather generalize the concept of a stress vector from being purely normal to having a general orientation. And this is what led ultimately Cauchy to propose the general stress vector and the general stress tensor, which need not be diagonal. But now we need a constitutive equation for the stress tensor. And this naturally leads us now to consider how the stress tensor behaves when a fluid is in relative motion. Because clearly, as we know today, and if one had experiments, then one could have found out that the velocity should go to zero at the walls. This even follows by reasoning, because it experiences drag at the walls, where it's highest at the center. So clearly, there is relative motion of the fluid elements in the pipe, and somehow this relative motion gives rise to additional stresses other than simply the normal pressure.